All right, video two. Let's talk about the main features of a wave with regards to how we can describe a wave's motion. At this level, it can get very complicated. We don't have to take it um, quite that far. But the first thing is frequency. Very similar to simple harmonic oscillation. It's the number of waves that pass a point in a given amount of time. So frequency equals waves over time. I always think of it as if you're a duck sat on a pond and six ripples go by you in 2 seconds, then you're going to have a frequency of 6 divided by 2. You're going to have a frequency of 3 ripples or waves per second. As far as the unit goes, it's waves per second. Although we don't really say waves, actually, we tend to say it as like 1 over s or s to the -1. And because that's a pain in the backside, we call it hertz. HZ hertz after hertz, I guess. And it's a scalar. I'm going to stop this slide in 3, 2, 1. Again, this is real similar to simple harmonic motion because whereas we talk about frequency in the sense of how many oscillations happen per second, we can also talk about period, which is how much time does it take for one oscillation to happen. Now, this is actually really easy to reason, and I forget if I put this in the other video. But let's say you got 3 hertz, right? There's 3 ripples go by, 3 waves go by every second. You're the duck in the pond, 3 waves go by every second. Well, when you think about it, it makes sense that the waves are going to be 1/3 of a second apart. That's going to be the period, right? It's going to take 1/3 of a second to go by because 1/3 times 3 is 1 second. And mathematically, when you reason that, you end up with this equation where period, capital T, equals 1 over the frequency. And I think that's it. No, it's not. It's seconds. It's time, right? So the unit is seconds, and again, it's a scalar. And I think that's all I have for this. So I'm going to pause it in 3, 2, 1. Okay, so now we know about frequency. We know that what wavelength is. If you remember, wavelength is a distance. If I'm just going to draw a wave with my finger, it's a distance from the top of one wave to the top of the next wave, or the bottom from one to the bottom to the next one. We know wavelength, we know frequency. How can we figure out velocity from this? And I think, again, that's easy to reason out if you think of numbers. Would be the same duck in the pond. There is a wave going by, it has a frequency of 3 hertz. That means that 3 waves go underneath the duck on the pond every second. Well, what if I told you that the wavelength between the tops of the one wave to tops of the other wave is 2 meters? Well, that means that when the first wave goes by, the wave has traveled 2 meters. The second wave after it goes by, it's going to travel another 2 meters, and the third wave goes another 2 meters. What's the velocity of the wave? Well, it's just going to be three waves with 2 meters per wave. It's going to be 6 meters per second. Let's just look at it here. I've got velocity equals 3 waves per second times 2 meters per wave. And when you think about it, the waves are just going to cancel out. So three um, this is waves per second, so this is a frequency, 3 hertz times 2 meters, and that is going to give me 6 meters per second. The long and the short of it is the velocity of a wave is equal to the frequency times the wavelength. Velocity equals F times lambda, and I forget if I said, forgive me if I did, lambda is the symbol we use for wavelength, F is the symbol we use for frequency. Lambda is kind of like an upside down Y. Okay, I'm going to pause this in 3, 2, 1. Okay, I want to talk quickly about waves and energy. I'm going to try and make a wave with this piece of string I just found. I don't know if it's going to work, but here's the thing. I have to oscillate this side. When I do that, I am doing work on this bit of string here, this side of the string, by applying a force over a distance. I oscillate it back and forth, and that energy transfers down the wave to the other side. The question is how much energy? What is that related to? And actually, it's easy to reason out when you think about it. Because if I am oscillating it slowly, not a lot of energy. If I oscillate it quickly, then I get a lot more energy. So what this is telling us is the higher the frequency, the higher the energy of a wave. Frequency is proportional to energy. There's no real equation we're going to need to know. We just need to know the relationship. So frequency is proportional to energy. And bearing in mind that the frequency equals 1 over the period, that also means that the smaller the period, the greater the energy. That makes sense. The shorter the time between oscillations here, the greater the energy in this wave. And I think the final thing is when we just think of this equation we just talked about, velocity equals wavelength times frequency. Well, the velocity of the wave as it goes down the string, you're going to have to just trust me, is going to stay constant. It's not actually, it's determined by a lot of things. For example, the tension in the rope, the size of the rope, other stuff like that. That's not going to change. But if I increase the frequency here, then I'm going to make the wavelength smaller. So again, we end up with 1 over the wavelength is proportional to the energy, meaning the smaller the wavelength as this wave travels down the string, the greater the energy in the system. Yeah, that'll do. All right, I'm going to pause it in 3, 2, 1. Okay, last little thing I want to show you. This is actually explicitly stated that you need to know by the AP chaps. Looking at a position versus time graph for a wave, what can we get from this this graphic? So this is a position versus time graph. I got the position, the Y position up here, and the time across the bottom. And what this is really telling you, how on earth have I lost the end of my piece of string? Here we go. What this is really telling you is, let's say we pick a point on the string, conveniently there's a little black smudge right there. As this wave goes by, it's telling us the Y position, not the X position, the Y position of this little black smudge, of this little point on the string over time. And so what information can we get from this? Well, what is the period of the wave? Well, think of it. One period is the time it takes my little black smudge, which I've lost, to go up, to go down, and go back to the middle. So the period of this wave is 0.02 seconds. What is the frequency of this wave? Well, if the frequency equals 1 over the period, and the period is 0.02, then the frequency is 1 divided by 0.02, and I think that's 50. I haven't got a calculator, but I'm hoping you get the point. So that's the information we can get from this. Listen, I'm going to do one last real quick video, much shorter than the last two, and then we are done for the day. Thank you very much, and I'll see you on video 3.